Hello all, welcome to my YouTube channel. Today I am going to discuss on a recurrent neural network and one of its variant known as LSTM. Let's get started. Recurrent neural network basically works based on the ant theory, where ant follows one after the other. So whenever we are having a data in a sequence, like a text data or voice data or audio data, so in that case we need a recurrent neural network. There are other neural networks like CNN, where CNN does not capture any sequence of information. To capture the sequence information, a recurrent neural network was introduced. This recurrent neural network can be used in natural language, can be used in speech data, time series data, video or music sequence data, and stock market data. Now let us look into the architecture of recurrent neural network. The main thing is that it takes input at a sequence over time t. At every time it takes a data and then it processes it and gives us an output. So this, when we look here, once the input is taken, when it is processing, the process information again is fed back to the neural network. So when I simply expand this particular simple architecture over here, I'll get a architecture similar to this. So when I process, say for an example x1, I'm giving an input over here, that is x1. It is getting processed at the neuron over here. When it is processing, it is taking the input from the previous state and gives us an output h1, and likewise it goes on. So this is useful when we have a sequence of data, or when the data is sequenced in nature, one after the other. So let us look in detail. This is exact architecture that we have seen in the previous slide. So if I want to compute any input at a given time xt, so I'm going to give xt over here, and it is, as you have seen, a neural network already, it is getting multiplied, input is getting multiplied with an some weights. Here the weight is denoted as u, and then it is getting processed at ht, whereas considering taking the output of ht minus 1, and even that is getting multiplied with some weights over here. So let us see how this ht is computed. ht is computed using some weight, that is input is getting multiplied over a weight called u, and then it is getting summed up with a weight into ht minus 1, that is previous state's input, sorry, previous state's output. And ht is, this is computed and it is fed into an activation function known as sigmoid activation functions. And then yt is computed. Once ht is computed, this ht is again multiplied with an weight known as v, and from there it is fed into a softmax activation function. From there we are able to get yt. So yt can be, again, say for example, if you are dealing with a language translation, so each word, when I pass it at xt, I'll get a word over here at yt. This yt is being a probability of n words, and that is the reason why softmax activation function is utilized over here. And during backpropagation, what I'm supposed to do is that I'm going to check whether the output at yt is exactly as what we have in our training data. To do check that, and to check that we are going for a, a cross entropy loss, that is j of theta is determined over at each yt. I'm going to take the value over what it has been predicted and what it has been actual value. So computing a loss function over cross entropy loss over here, I'll be able to determine how well how well my model is able to work for a sequence of data. Again, if the loss is higher rate, I'll try to reduce it through number of trainings, and here the back propagation happens through back propagation at time. We call it as BPTT. Let us see how this works. As we have computed the hidden state HT, where the weight input is getting a previous state in output is getting multiplied with an weight, and it is getting summed up with what is the input at xt. Again, it is getting multiplied with an weight over here, and yt we are getting, or yt hat, we take ht as an input over here, and we get multiplied with a weight over there, and we pass it into an activation function. So I compute, once I compute my yt, I'll check what is my loss. And how do I compute my loss is that I'll find derivative of loss, that is error, with respect to my weights. Here we have seen that three weights are available here, that is u, v and w. These weights are going to be same across the entire neural network. As we seen neural network already, we have we told that a random weight be allocated, and these weight will be adjusted during back propagation. So here the weight is going to be the same. So when I compute the final element yt plus 2 during back propagation, what I'm supposed to do is I'm going to compute what is the value of v, what is the value of u, what is the value of w, and these w again, it depends on the previous w. I am supposed to compute what is the value over here, and this w again, it depends on w over here. So the toughest job in RNN is updating this weight through backpropagation. This can be computed through a chain rule application. So I'm going to compute my weight loss with respect to weight. So I'm going to compute a derivative or partial derivative with respect to loss, and that particular loss depends on yt, that is my output. Yt is depending on my ht, that is my hidden representation. Hidden representation again, it depends on previous hidden representation, and previous hidden representation depends on my weight again. So using this chain rule, I'll be able to update each weights. So moving on further, let us look into the types of RNN. It can be a single input is being set to an neural network, and you can have one output. The next architecture is one-to-many RNN. In one-to-many RNN, I'll pass only one input, and I'll have sequence of RNN, that is hidden state, and I'll get multiple outputs over here. So this happens in a case like an image captioning. In image captioning, I'll have a single image as an input, and for that particular input, it will give me a detailed description, that is a captioning. So the captioning is not in a single word, it will have multiple words over here. So it is 1 to many RNN. Moving further, many to 1 RNN. It means that I am going to have multiple inputs but a single output over here. That happens in a sentiment analysis where I'll be passing my input will be in the form of an many sequence of uh, input at different time, and the response will be a single response. That is, either since it is a sentiment analysis, when the sentence is given, that particular sentence is a positive or negative or neutral, so I'll get only one response out of it. So it is an many to one RNN. And speaking about many to many RNN, where we have multiple inputs and we are having multiple outputs. This happens during machine translation. Moving further, the limitations of RNN is that during backpropagation, that as I told you, it happens through backpropagation, happens with respect to time. So when it happens, so it will face a vanishing or exploding gradient. Either during gradient, the variables may be shrink or it may exponentially grow up. Because of that, we will not be able to end up in a local minima. So that again, the error is going to be very high. So that is one limitation with RNN, that is vanishing and exploding gradients. And the second thing is that when we have a long dependency in a sequence, RNN struggles to capture those information. The previously spoke information will not be available after a large sequence has been processed in RNN architecture. To overcome that, we are going to see one architecture known as LSTM in the next slide, and GRU is also available. The third limitation is that since it is dealing with a sequential information, RNN by basically it takes more time to process.